Hello everyone, and thank you for having me today. And I'd like to talk a bit about the journey I went through building a serverless e-commerce platform. So my name is Nicolas. I'm a solutions architect at AWS, passionate about serverless technologies. And as part of my job, I have the chance to interact with lots of AWS customers and lots of customers building very interesting things using serverless technologies. And seeing these different customers, I've kind of seen trends, patterns, things that worked well, things that didn't work so well, and so on. And I wanted to have a mechanism that I could use to share these learnings in a repeatable manner. So I set myself to create a sample e-commerce platform just to showcase some ways that you can build a large-scale serverless application. And to get started on that, I'd like to start with a quote from No Silver Bullets by Brooks. If you haven't read it, it's a really interesting paper. So the quote goes like this: "Of all the monsters who fill the nightmare of our folklore, none terrify more than werewolves, because they transform unexpectedly from the familiar into horrors. For these we seek bullets of silver that can magically lay them to rest." And so in this paper, there are two concepts that are very key, I think, and very key for this talk today. And that's essential complexity and accidental complexity. Essential complexity is the minimal set of complexity in a software that you cannot get away with. So if you have specific requirements, a user wants to do A, B, C, then you need the complexity to be able to accomplish these three tasks, the three tasks A, B, and C. You cannot go below that, you cannot remove that. The accidental complexity is the rest, speaking broadly. So it's all the rest in terms of complexity. That's all due to the technologies we are using, that's due to the way we structure our project and so on. There's always going to be some accidental complexity, but over time this actually been going down. If you think about the history of computer science and computers in general, we started with this big large machine that we had to configure manually. We had these punch cards, we had assembly, then we started having higher level, order level languages. At some point, C was considered a high-level language, and nowadays, C is considered as a very low-level language because we have all these new layers of abstraction on top of that helps managing this accidental complexity, that helps, from all points of view as software engineers, reducing the complexity that we need to take care of. And now with cloud platforms, there's also more and more of the accidental complexity being managed by the cloud platform to simplify what we need to think about. And for this, I'd like to take an example of two AWS services. Amazon DynamoDB, that's a NoSQL storage solution, where you create a table, and then you have just an API that you access, and you use that to create, remove items, update items, search for, filter and so on, these items. And that's basically it. The table itself doesn't really have, there's a physical limits, of course, but it doesn't have, there's virtually no limit on how much data you can store on a single table. And you just have this API to consume, so it's very easy to do that. Another service here is Amazon EBS, or Elastic Block Store, which is a service that offers a block device when you run EC2 instances. So when you use EBS, you have it, you create a volume, and this appears as a physical volume to your instance. But both of these services are storage services in a distributed environment. Highly available, it needs to be highly available, needs to be highly resilient, and building distributed, highly available data store is no easy thing. There are lots of problems. There's the CAP theorem as well. And the EBS, the link I put there about the EBS is really interesting if you want to know how EBS addresses the challenge of CAP theorem at scale. So these are very complex problems to handle. But the fact that for a developer, for someone using the service, you just have these APIs that you can use. And all that complexity is hidden away and managed by the cloud platform is quite powerful because it enables to focus more onto the essential complexity and therefore do more. And in a way, serverless is very much about that as well. And the first aspect of that is the fact that on the infrastructure side, you don't really need to provision or manage the infrastructure. So if I take a service that's used a lot to build serverless application, AWS Lambda, which is serverless compute service, you provide your code, and then you configure the permission when that code executes, you configure the events that triggers that code, and that's it. When events are coming in that match, that trigger that code, the event could be an API, could be a reaction to something else happening in your infrastructure. This will trigger the code. And the cloud platform will take care of managing the infrastructure underneath to make sure that your code can run. And that leads to a few other benefits like automatic scaling, meaning that within the bounds that you define within your account limits, you can have a certain number of execution environment that will run that code, but it's not yours to be concerned about. If automatically you need more because there's suddenly a surge in traffic, it will scale up to meet that. And another aspect is the pricing model of these services. So in the case of Lambda, you pay per execution and per execution time. So if you don't have traffic, or very low amount of traffic, then you pay nothing or almost nothing. But then if you have a surge of traffic, you pay more. But that usually ties into a business value, because if you have a surge of traffic, it might be because you have a surge of visitors to your website, you have a surge of users. Therefore, there's kind of there can be a correlation between the two. And finally, because you just provide your code, the cloud provider is now responsible for managing the rest of the infrastructure. So that goes from the physical host, of course, that's a given in cloud. So if there's a problem with the physical host, it will make sure that replace the underlying infrastructure. But it's also responsible for patching the operating system, for making sure that the service itself is secure and so on. These are regional services, so make sure that it's highly available in multiple availability zone in that region, and so on. So because all you do is provide your code, and you just expect AWS to run it when it needs to run. And so that means that you have less concern in terms of how do I make it highly available, how do I secure it. You're still responsible for some part of it. If there's a bug that brings down the availability in your code, or if you have a vulnerability in your code, that's still your responsibility. But the surface area is greatly reduced here. And so if we focus a bit more onto the essential complexity, and now I'm going to go a bit deeper into the e-commerce platform that I built. What is the minimal set of features that you need to have in an e-commerce platform? At a high level, you have that. So the user needs to be able to look at products, then they should be able to make an order. Once an order is made, someone needs to take the items for that order and package them, so that afterwards someone can ship them. Might be the same person, might not be the same person. Then we need to track the whole flow. First of all, the user would like to know what's the status on their order, but we also may need to make sure that we are not missing something, that there's not something lost and so on. And finally, we need to process payment, right? It's an e-commerce platform, so we sell things, therefore we need to get paid at the end of the day. And so you can see on this, the complete application on this GitHub repo, and also put a QR code if it's easier for you. And so if you look at the flow, it's a very simple order flow. I'll be very honest with that. And there's also very different ways to design an order flow depending on the premises that you take. But if you think about it, here we have the user. The user should be able to register, log in, log out. And then they should be able to search for product, find the products they want, and based on that, create an order. Once the order is created, in the warehouse, we need to create a package from that. So package all these items into one package. Then on the delivery side, we need to ship it. We need to track the shipment until it's delivered. And once it's delivered, we can mark the orders complete and we can process the payment. And so that's kind of the basic flow. There are, of course, different ways to do that. For example, here I'm processing the payment at the end. You might want to process it earlier in the flow and then manage the failure path differently. And speaking of failure path, well, sometimes things fail. And here I'm not even talking about the technical failures. I'm talking about the business level failures, such as the items not in stock, or we tried to deliver, but the address does not exist, or the person did not pick up the package, and the package was sent back to us. What do we do from that? Well, then in this case, we cancel the payment and we mark the order as cancelled. So see, if the item is not available, we just don't ship it. We don't wait for it to be back, to be available again. But then you also have more complex failure modes, such as if you have an order with 8 items and 7 are available, but not the 8th one. Well, we can still ship the 7 first ones. There might be a substitute for the 8th one. And so if the products in the package do not correspond to the products in the order, we'll update the order. If it's resulting in being cheaper in total, because we remove an item, we update the payment information. If it's more expensive, we don't charge the user more because they didn't choose to pay for the more expensive thing, so that would be a bad customer experience. And finally, you can't trust user input, so when a user is creating an order, we need here I'm doing synchronous calls to validate that the product information is correct, we can deliver to that address, and that the payment token that the user provides is also valid. So here that's kind of the gate between untrusted user input, and then now we are trusted part of the flow kind of way. And so all of these boxes here, the different colors, correspond to different microservices within the application. There's a bit more than that that's not shown in this flow here, but that's part of the accidental complexity that you can never really reduce to 0. But if we start zooming in a bit into one service, so let's look at the order service, and I'm just going to reorder a bit the flow here. So there are a few different things here. So there's the events, so that can be user creating an event, an order. That can be that we could not package all the items, could be something went wrong, or the order was delivered, it was fulfilled. This should trigger an action from the order service. And out of these actions, we should either emit an event again, so if other services need to consume it. Let's say when an order is created, the warehouse service needs to know about it, so they can start packaging that. We also need to persist that data, because users or other microservices might want to query and know what's in that order, what's the status, and so on. And if I were to kind of draw boundaries here, just to make it easier to map to the AWS bits, so in gray we have the flow where the user is creating the order. In purple we have the reaction to events. In green we have the state storage and query. And in red, we have the output when we send an event back. And so if we look on AWS, what it looks like, that's the architecture diagram for the order service. So in green, I'm using DynamoDB. I'm using a table there that I mentioned DynamoDB before, so as an SQL database. And when I need to make a query, I have a service called Amazon API Gateway that provides me with a REST API. This triggers a Lambda function that fetch information about the order. And so, for example, here the delivery service needs information about the order, so they can do that. If we look at the gray part, so the create order flow, then I have the front-end service. It's a single GraphQL API that's fronting all microservices for the users. This one will trigger Lambda function. The Lambda function needs to check with other microservices, so in this case, products and delivery pricing, contact their API gateway, so their REST API, to kind of validate the information. If it's all good, then it stores into DynamoDB. If not, send an error message back. In purple, there I'm reacting to events. So for events management and centralization, I'm using a service called Amazon Event Bridge, which provides me with an event bus where all microservices can submit events. And then I can define rules to subscribe. So here I'm listening to 4 types of events, 2 from delivery and 2 from warehouse, when it's either the delivery was completed or failed, or the a package was created, or the packaging failed. And this will trigger a Lambda function, which, based on the type of event, will update the data in DynamoDB. And then once you have an update, we get into the emit event part of the flow. DynamoDB has a feature called DynamoDB streams, and this stream all the changes that happen to the table. So I have a function picking that up and transforming it into business events, because I mean, I don't want to submit to a bus used by different microservices technical level events. I'm going to translate that into something that makes sense from a business point of view, such as order created, modified, deleted, cancelled, and so on. So how does this single service fit into the overall platform? Well, you've already seen that in terms of communication, there are two services that I use between services to communicate between microservices. So one's for synchronous communication, mostly when I need to request something immediately, I need a response. So such as fetching data, or I need to validate that something is correct. And then I have the other case for asynchronous flows, where I just need to submit an event and microservices are responsible to subscribing to them to the right event. So for this, I'm using Amazon API Gateway, provides me with a REST API, and Amazon Event Bridge, where I have this event bus where I can submit events. But that's not really all there is. If you think about communication across services, such as, you have questions such as, how do I find that API? How do I make the right API call? How do I know, what query I should make? When I'm using Event Bridge, how can I consume a message? How can I consume a message from the right service for the right event? And what's the message format for that event? And that kind of leads me into the aspect of types of contracts. In microservices, you have contracts between microservices. And what I've found is that you have two main types. You have the platform level contracts and the service level contracts. Platform level contracts are things that should be agreed on by all microservices. So in an e-commerce platform, there's kind of a shared vocabulary. There are things that make sense throughout the platform, and we should kind of agree on what it is, what's the name, and so that we don't have that confusion between different microservices on how we call things. If one's calling product, and the other one's calling it item, and the third one's calling it object, that might be confusing because we might not be speaking about the same thing. Then there's an aspect of how do we do service discovery? How do we structure services? What tooling do we use to some extent? I'll get a bit into this bit later. Then on the service side, you have what's the responsibility of the service team. So if you have a project that's large enough where each service has its own dedicated team, they are responsible for what they present to the world. The schema they use, to some extent, and we'll get to that, ties a bit into the vocabulary piece. But also, what do they expose? Do they need to expose the REST API? Maybe not. Do they need to send that event to the bus? Maybe not, but that's up to that team to make this decision. And they might have another team saying, oh, we need that data from you. Then they need to do that. So if we go into the platform level contracts, first of all, why does it matter? Why can't every service team just do what they want? Well, if you think about it, it doesn't really matter if services are using languages like Python, Java, Haskell, as long as it's maintainable, well documented, and someone else in the company knows that language. Because if you made a microservice in Haskell and you're the only one in the company that has Haskell and you are leaving one day, what do we do now? Do we hire someone who knows Haskell? Do we rewrite it? We need to understand what it does. It might be a tricky situation. So there's still some restriction here, but it doesn't matter in the bigger scheme of things. But if one service is using Zookeeper, and another one DNS, and a third one is using a NoSQL database as service registry, not as data stores. This adds additional complexity, because now when a service team needs to consume your service, they need to think, oh yeah, that service, what's its mechanism to know where to find it? Should I use DNS? Should I use Zookeeper? Should I use something else? So that just adds complexity with no real benefit. Having a central way of doing serverless discovery, for example, simplifies a lot, because everyone understands that's how I should publish information about my service so people can find it, and that's how I should consume it. It makes it much easier. And for this, I've used a service called AWS Systems Manager, and it has a feature called parameter store. It's a simple key value store, and that's all I need for service discovery, really, where you have a name and you have a value. You create a name, you get the value. So In this case, there is a convention on names as well. And that's kind of the naming pattern here. So /e-commerce for the e-commerce platform. And then you have the environment, such as dev or prod, and then the service name, for example, orders, and then the name of the resource and the type of the parameter. So, for example, e-commerce dev orders API URL, that's the URL of the API from the order service for the dev environment of the e-commerce platform, and so on, so on, so on. And you know, so this way, if I'm in the dev environment, I'm another service needing to consume the orders API, I know what parameter to use. Another thing that's been quite important on service discovery is using infrastructure as code. And it's not important just for service discovery, it's important in general, just because you see you have all these building blocks and a way to orchestrate these building blocks so that you can deploy them in a consistent way is very, very important. And for that, there's quite a few tools. I'm more concerned into people using infrastructure as code with specific tool they use. So there are three main generic ones, which is Terraform, AWS CloudFormation, or AWS CDK. In my case, I've been using AWS CloudFormation. And then you have some that are more specific. So the ones I mentioned in the bottom are more specific to serverless, with all kind of having their own twist. Serverless is a bit more generic. Some, which I'm using to some extent, is an extension to CloudFormation, as in what you do in SAM you can do in CloudFormation, but SAM has extension to CloudFormation that are specific for serverless, and that simplifies a lot the flow when you're building serverless application. So that's SAM and CloudFormation, that's what I'm using mostly for this project. And so in this case, in CloudFormation, you have this, you create a template, it can be YAML or JSON document, and within that you can have this parameter section, which is basically the input when you deploy, when you create a stack to deploy the resources to AWS, you can set up the parameter values to kind of define what should it be. And in this case, for example, if you look at the event bus name parameter, it has a type of AWS SSM parameter value. That means that when I'm doing the deployment, I just need to pass the name of the parameter. I don't need to pass the value. And CloudFormation will take care of resolving the value from the name so that I don't need to do it myself. And so I can just pass the name and then change it based on environment and so on, and it will get translated at deployment time. And then from that, I can use it as an environment variable in my code. So here I have the global section, which is a SAM extension. So in this case, it allows me to define default parameters for my Lambda function, such as Python 3.8 or a timeout of 30 seconds. And also here, all Lambda function will have an environment variable called event bus name. So if they need to send an event, they can just use that environment variable to know to which event bus to send the data. So that simplifies a lot the flow. Another thing that can do from that is use it to scope down permission so that, for example, a Lambda function will just have the permission, in this case, to call a specific API. So I mentioned the API URL parameter earlier, but also it can expose an API ARN, Amazon resource name, which is used for identity and access management. So I can use that to scope down permissions so that here I can, I'm only allowing to do a post request on delivery API. So that's a good way as well to kind of communicate this kind of information. And that kind of brings me into the types of parameter injection. And I see really two types. Here I talked a lot about the deployment type. So you inject in the infrastructure as code, and the values are updated during the deployment process. The good thing is that once it's deployed, there's no cost to performance impact because it's bundled together. So my Lambda function has its environment variables there with the Lambda function. So that's one less thing that could fail in the overall process. The function does not need to call a third-party service or anything like this to do that. And that's kind of well suited for things that don't change often. So the API endpoint, the event bus name, these are things that will probably never change for the entire life cycle of an environment. But then you have other cases. And for that, you have the possibility to do add runtime parameter injection. So here you could do Every time you initialize an execution environment, or let's say every 30 seconds you need to refresh that data. And so every time it will query a service, it can be the parameter store again, to kind of refresh value. And that's good for things that can change rapidly, but it introduced the fact that now if that service failed, what do? You need to think about that failure mode. But that's really good for things like feature flags, circuit breakers, and so on, things that can change very, very fast. And so another thing about the platform level contract is the shared language that I teased a bit. And that's, everyone should kind of agree within the e-commerce platform on what a product is, because it's such a key part of the e-commerce platform. So we should have an agreement on what's a product, what's the definition of a product, but also what information it contains. And the thing here is that what makes sense for the e-commerce platform might be different for the business units. For example, the picture of a product doesn't really matter for the business analytics. But on the business analytics side, maybe you want to know what's the profit margin, what's the cost of acquiring that product, and so on, what the cost of storing that product. There are lots of other information that are pertinent there, but the e-commerce platform is solely concerned with getting order and fulfilling them. So the definition of product might be different there. And so a great way to agree on that is to have some form of schema with description, documentation, examples, and so on. So it could be JSON schema. In my case, I'm using OpenAPI schema. And so that kind of leads me into the service level contracts. Now, when it becomes the responsibility of the team. So we have agreed upon the way to deploy, the way to share parameters and do the service discovery. We also agree on certain semantics. And so I mentioned that I'm using Amazon API Gateway and EventBridge a lot, and there's a really neat thing with both of these services that they both support OpenAPI documents. That means that I can have code, contracts, and documentation at the same thing. Because when you want to deploy an Amazon API Gateway or REST API, you use an OpenAPI document. I mean, you can use an OpenAPI document. But an OpenAPI document is documentation. And because it's the one that's used to deploy things, it's proof of contract. Because I can just go to another team and say, hey, look at this OpenAPI document. That's the one we use to deploy our resources. Therefore, that makes it easier for them to have a kind of level of certainty that, that's what happens. And the thing here is that I can rely on the shared language. So I can do a reference to a shared resource with the shared schema resource. So this is the pricing validation to validate the cost of deliveries. It needs to receive a list of products because products have packaging information. And therefore, in the request, I can say, you need to send me products. And what's a product? Well, we have this shared schema on what's a product, so you can just use that. And for EventBridge, it's kind of the same thing. It's also using OpenAPI schema for the events emitted by a service. So I can also show to other team, hey, that's how it is. And within EventBridge, you have the schema registry that can be used for things like producing code artifact for a specific schema. And once again, I'm using this shared vocabulary. So the package created will contain the list of products in that package, and therefore, once again, we need to know what's a product. And speaking of shared resources, I'd like to just make a quick digression on shared libraries, about finding the middle ground between what should be shared and what shouldn't. And what I found that works really well is that share libraries as a convenience, but something that's disposable, something that services don't really need to use if they need to, work quite well. So it's something that's changed slowly and works around either AWS services that lots of teams are using or shared semantics. So in this example here, that's something that wraps around API Gateway. So when a Lambda function receives an event from API Gateway, it comes in a specific format, and API Gateway is expecting a specific response. So I have this response function And this will just make it easier for teams to quickly spin up responses, quickly send responses, in a way that's well-defined, well-formatted, and so on. So with the course headers and these kind of things, they don't have to worry about these kind of things. That's easier for them to consume. So that's quite useful. Because that kind of brings into the trade-off between the reusability and the flexibility. So, it's the question of how many times a specific piece of code will be reused across the board, across multiple microservices. And the flexibility piece, which is what's the probability that one specific service needs to change the code for their context. And now we get into the boundaries of ownership, because when it's something that's shared, how do we make sure that it doesn't spin out of control and so on? Who maintains it? Does it make sense for the platform team to own it, or does it make sense for the service teams to rebuild it and own it? Because now someone's going to be responsible for that code. Code is a responsibility. It's a liability. And so now that we have all this piece and so on, let's talk a bit about the orchestration and how we get all that into production, basically. And how do we orchestrate all these different components together? How do we merge them into one system? So for this, I've been using a monorepo. And monorepo has its pros and cons. I've seen customers using both monorepo and polyrepo approaches very successfully. In my case, it was very, very convenient because since it's a sample application, I can just say, hey, here's the GitHub repo. I don't have to tell you, hey, look at these 12 different repos. And with it, each service has its own folder, and there are some folders for shared resources. So, for example, the schema and so on, and tooling. And so, what's a service? What makes the core of a service? And it's really two files. It's a make file and a metadata.yaml file. And the reason why is, so I've seen two kind of approaches for orchestration. One's that I call paved path, and the other one I call fenced path. So what's the difference between the two? In the paved path approach, you have some guidelines, some standards, some templates for common use cases that people can reuse. But ultimately, every microservice team is able to escape from that, is able to use something different. And you have this configuration of a convention. You have a base, so if you stay on the path, in my case it's CloudFormation and Python 3, then it's super easy. There are lots of templates and lots of things that you can just reuse out of the box. There's this shared library and so on, that's neat. But if you want to use something else, if there's something better for you, then you can use the right tool for the job. You are free to go beyond that. In the fenced path approach, it's a bit different there because you enforce one way to do things. And that leads to fewer chances to make mistakes. And it's easier to onboard developers. It's easier if you have junior people that need to learn and so on. Like, you minimize the chance of mistakes. And you enforce a specific convention over giving a freedom for configuration. But that comes often with a downside of now you need to have a central team to ensure that we give the maximum flexibility of developers anyway. So, but these two approaches are not one or the other. It's kind of a spectrum between the two. And the paved path approach, well, the platform team has less possibility, you have more flexibility, but you have a steeper learning curve, longer learning curve, and product team also responsible for more bits as well. And the fenced path is kind of the opposite, but you end up somewhere in the middle. So in my case, because I have CloudFormation and I have this makefile, I'm actually giving a lot of flexibility, but there are still some common bits that are shared, agreed upon. I need CloudFormation at some point in the process, and we'll get into that into the CI/CD pipeline. We agree on a specific way to do service discovery and so on. So there are still some ways that are guardrailed. And so if I go back into the service, I mentioned it's makefile and metadata. So why makefiles? And the key thing is that technology evolves. And if you look at the history of AWS and at the pace at which there are innovation and so on, there might be a better way to do things tomorrow. I'm not wise enough to know how things are going to look like in the future and if there's going to be something better. So having this escape hatch, having a way to decouple things, allow the architecture to evolve. So that today we might use CloudFormation, serverless, Python, and so on. But maybe in the future there will be something else. Maybe there will be something better than Python to use in our use case. Maybe there will be, maybe CDK will be better than CloudFormation. I don't know. Or maybe for one very specific use case, serverless might not be the right thing. I don't know either. So I need to kind of keep the door open so that I can make this change in the future. And so the anatomy of a makefile kind of reflects that. There are some specific targets that a makefile should implement, such as building, packaging artifacts, deploying, tearing down the resources, running tests, and these kind of things. And as part of the paved path approach, there are pre-built makefiles for common scenarios. So I mentioned CloudFormation and Python is used a lot. Therefore, there is a makefile that just does that. So if teams are using CloudFormation in Python 3, they can just copy and paste that makefile, and they are good to go. And then you have the metadata file, and this contains information about the name of the microservice, its dependencies, which is very helpful for when you're deploying resources. And then parameters. So I mentioned the parameters in CloudFormation, and then here I have the parameter store name for it, with environment being a variable that gets dynamically injected, depending if I'm on the environment I'm working on. And then when I put all the pieces together, I have a central makefiles from running some of the commands. So I can do things like make all orders, and that deploy the order service. Or I can do make and then use environment equals something, and that will deploy all the services in a specific environment. So feature 1, 2, 3 if I want to use one environment by feature. Make teardown will tear down all the services, will remove everything from the AWS side. And then I can also do very specific tasks, such as running the integration test on the order service, for example. And so if we zoom a bit into this make all order piece, it does a few things under the hood. So it first starts by limiting the code and templates, making sure there's no stylistic mistake. You can also have some custom rules, which I do for CloudFormation lints. So CFN lints is a really good tool for that, and you can create your own custom rules. So I can enforce some things here. Then you build the resources, run the unit test locally, so run the unit test on the code. Then check that the dependencies are deployed, because otherwise deployment will fail if you don't find the right parameter value. Package the code artifact, the CloudFormation template, everything, getting it ready for deployment, deploying it, and then once it's run AWS, you can run the integration test. And these 3 bits here, the fact that every time you do this kind of operation, you do this check, this sanity checks and so on, that makes it easy for developers to write high quality code. And another thing that goes with it is that in serverless, everyone can have a replica of the prod environment. Because if I do make, by default the environment is dev. And if every developer has its own AWS account, then it means that every developer could have a replica of the prod environment. And that's not just a replica as in, it's the same code base, but it's configured the same way, the permissions are the same, so we're testing way more things. We have the capability to test way more things. We can also test traffic, because whilst you don't have much traffic, it's very cheap to operate, and that's really good, but it might cost pennies or less per month per developer to have this environment there. But let's say now you need to test because there's a bug that only happens when you have a specific amount of traffic. Well, you can just use a load generator, generate load for 30 minutes, and run that, check that, and so on. And when it's done, you stop the load generator. The infrastructure is still there, still configured the same way. That's a really great way to validate, because you validate on something that's as close as prod as you can get, because it's actually running on AWS and actually configured in the same way. And on this kind of flow, I'd like to talk a bit about the different type of tests. And so the integration tests, you've seen them, they are running on AWS actually. And they validate the contract, they validate the permission and so on. So for example, if we go back to the order diagram, I have this event. If I have an event that will result in order being cancelled, I can send that event to the event bus, and then I will check the DynamoDB table and see has the order been cancelled properly. And then I can check back on Event Bridge and see did it submit the right order cancelled event. And so I have a pretty good guarantee that it's working as expected. And they're a bit slower because now it needs to run, especially here on asynchronous workflow, I need to kind of wait a bit to make sure everything is processed. But they're very precise because if I have a bug in my code, I could catch that earlier, but it will also catch errors due to permission error and so on. So it can catch way more things. It's way more precise because it's actually behaving. It's actually testing the way it should work, testing the contracts. Then on the unit test side, that's where you just test the code based on contract assumption. So you assume that the service will behave this way, that it should behave this way. And it's faster because it just runs on your local machine. You don't have this whole cycle of deploying. But because of making assumptions, because when you're mocking and so on, you're making assumptions on some aspect, you're assuming that your permissions are configured correctly, you might make mistake, yeah. But the integration test will help you catch that. And you get a bit into this complete flow here for the developer flow, where you pick a feature you want to implement, you write, modify the integration test, you write the unit test to correspond to this integration test, and then you write the code to correspond to this unit test. Then you run the unit test, does it pass? If no, what's the cause? Is it the code or is it the test? Because test is code, therefore you can have bug in your test as well. And then you go fix what was wrong, test again until it passes. Then when it passes, you deploy to the developer sandbox, you run the integration test, and does it pass? Yes, no, once again. And the good thing here is that you have these 3 layers of code. You have the integration test, unit test, and the code itself. Something in the middle could be wrong, but because you have these multiple layers, you basically test the test at the same time. So that limits also the risk for errors here. And so you go through that flow until everything is green, and then when it passes, you can push the code, create a pull request, and then you have the classic process until it gets merged into master. And once it gets merged into master, here's kind of the pipeline to production. And I think here it's important to mention, so I've been using a monorepo, but I wanted to showcase something that would be both relevant for monorepo and polyrepo. So I'm using a few services here. The first one in the flow is code commit, which gives me a Git repo. And once there is a commit to master, this will trigger a code build. Code build is a build and test service. You just provide the build specification and it will perform the task that you want it to do within a Linux container. So here it will detect the changes, which service has changed, and then run all the operations, so lints, unit test, package the template, create zip artifact, and store this zip artifact onto a simple storage service, or S3. And then from there, when a new object is put on S3, this will trigger the service deployment pipeline, and each service has its own deployment pipeline using a service called code pipeline. And the first thing it does is deploy to the test environment, run the integration test for that service, then deploy to staging, and then I have another layer of tests, which are the end-to-end tests, and these test the flow from the user perspective, as in and internal or external users. So if you make an order, it will test, can I create the order? Can I search products? Can I create the order? Does the order happen? Can I pick it up from a warehouse side? Can I create a package from it? Okay, now that I have a package, can I pick it up from the delivery side? Can I create a shipping for it? Can I track the shipping? Can I mark the shipping as complete? These kind of things that are getting tested there. And I can test the happy flow, the unhappy flow, and all these things in between. And when all of these has passed, then I can deploy to production. And as you can see, there's quite a few layers of tests in this workflow, because the whole point is minimizing failures that are going to production, right? And because even though I already do some tests locally, because it's part of the developer's responsibility to testing. Nothing is preventing a developer from pushing code that without running the unit test or the integration test, or even then maybe they didn't run the end-to-end test, which they could also do in their own environment. So this really catch things to make sure that this is validated. And also you have a few other things on that, because you might say, the unit tests are not covering everything, but that's part of, first of all, I have a code coverage minimum requirement there, but it's also part of the pull request process of the code review and so on, making sure that everything is correct. And with that, thank you very much for your time today. Hope it was useful. And once again, here's the link if you want to kind of dissect that. If you want to give me feedback, give me your thoughts, if you have any question, feel free to reach out to me on Twitter at @Moutschen. Also, pull request issues and so on the Git repo on GitHub are very welcome. And thank you very much for your time today.